Okay, to solve the examples, we need to understand some terms used in the analysis. Okay. Okay, the first one is VC, which is the average speed of the carrier, in this case the AGV. Then we have VE, the empty speed of the AGV. Basically, the speed of empty AGV can be faster than when compared to when it has a load. However, the programmer can set a fixed speed, okay, which make the VC and VE equals. But in some cases, maybe there are difference. The next one is loading handling time. So basically, this one is similar like this one. So I will use TL, okay, for load time at the load station, and then I use TU for time to unload, okay, at unload station. So I won't use the TH, instead I will use TL. Then we have destination distance, okay. So this one is when the AGV move from loading station to unloading station, okay, what the distance between these stations. And then empty move distance is when the AGV move from unloading to loading station. Then we have a traffic factor, which is the time that incur because of the blocking of vehicles or operators, okay, during the operation of the AGV. For example, when there is a operator cross in front of the AGV will naturally stop, okay, to avoid the collisions. So this will account for the traffic factor. So normally the traffic factor lies between 0.85 and 1. Then we have the handling efficiency, okay, availability, and the worker efficiency. Okay, this is how the efficient of the worker or the operator to perform the loading and unloading materials from the AGV to the station. Next we have the RF, which is a specified flow rate of the system. Okay, the unit is delivery per hour. Next we have a list of equations. Okay, so cycle times is the time where the AGV needs to complete a task. Okay, for example, it moves from loading to unloading station. After it unloads the materials, it goes back to the loading station. So once it reached to the loading station, this one, the AGV has completed one cycle of the operation. So the time for this one we call as TC. And then we have available time. Okay, how much time that the AGV available per hour. Okay, so the unit is minute per hour. Rate of delivery per vehicle. Okay, RDV equal to available time over the cycle time. So the unit is delivery per hour, and the workload is equal to RF and TC. So this is a minimum hour and this is the unit of minute per hour. Okay, the amount of work that must be accomplished in 1 hour. and RF is the delivery per hour. And then we have a number of carriers, NC, which we want to determine how many carriers that we need to have, okay, in order to complete the specified performance. Okay, so the formula is workload over available time, which is equal to RF over RdV. So again, RF is the flow rate of the system, delivery per hour, and RdV equals to available time over TC, the cycle time. Alright, so for the first example, we have AGV, okay, that move along a route. Okay, so given the AGV layout in the figure and the info listed, okay, this is the info provided. Determine the number of vehicles required for a delivery rate of 40 delivery per hour. So in this question, it wants us to determine how many AGVs, okay, that can satisfy this requirement to have 40 delivery per hour. Okay, so the info given are loading time TL, which is equal to 0.75 minutes. It means that the loading time here to load the AGV with materials takes about 0.75 minutes, around 45 seconds. Okay, the unloading time, okay, is 0.5 minutes, about 30 seconds. So the time required by the operator to unload the material from the AGV and put it in the station. The vehicle speed, VC and VE is similar, which is 50 meter per minute. Okay, the availability equal to 0.95, means about 95% is available. Okay, driving factor 0.9, the worker efficiency 1, and the destination distance LD, okay, LD is from here, here, and here. Okay, so basically this one is around 35, because 55 minus 20. Okay, this length is about 40 given here, and again this one is 35. So these numbers add up together, we will get 110 meter. And for the empty move distance, LE, it move from the AGV will move from this point to this point to this point. So we know that this is 20, this is 20, and this length is 40. So these distances add up will become 80 meter. Okay. So now we have all the formulas, all the information. Now how we can determine the number of vehicles. So we back to the formulas. So to determine the number of vehicles, we need to use this formula. Okay, so we need to find what is the workload and what is the AT, the available time. So the workload given is given by formula of RF times TC. So we need to find the TC. So TC is equal to this formula. Okay, so in the first place we have to determine what is the TC. So it is the loading time plus unloading time plus distance over speed. Okay, and distance, empty move distance over speed, and then we got the cycle time equals to 5.05 minutes. And the workload equals to delivery, okay, desired delivery times cycle time, okay. So 40 is given, is the desired delivery given by the question. So these two numbers multiplied will result in 202 minutes per hour. So this is the workload. And then for the available time, okay, we use this formula: 60 times availability times the traffic factor times the efficiency. Okay, so we have 60 times the availability, the times the traffic factor, and then the efficiency. So we get this value. And lastly, the number of vehicles equals to workload over available time, which is 202 divided by 51.3. We got 3.94 vehicles, or approximately 4 vehicles, okay, required in this system to have a 40 delivery per hour. Okay, in the example 2, there is a layout given to show the direction of travel of the AGV, okay, from station to station. So there is a 5 station: station 1, station 2, station 3, 4, and 5. Okay, and there is a form to chart, okay, to indicate the flow rates and the travel distance, okay, from one station to another. So before that, let's read the question. So based on the layout given, the form to chart in the next page determine, okay, please determine the average delivery distance, LD. So we have to find the distance, okay, average delivery distance, LD, and there is a specific formula for that. Okay, before that, we can try to read the following statement first. Okay, the AGV include load station 1, where raw parts enter the system for delivery to any of 3 production stations, 2, 3, and 4. So 2, 3, and 4 are production stations, and the 5th one is a unloading station, which receives finished parts from the production station. Load and unload time at station 1, 5, and load and unload time at station 1, 5 are each 0.5 minutes or 30 seconds. A complicating factor is that some parts must be transferred between station 3 and 4. So some parts are delivered from 3 to 4. Vehicle move in the direction indicated by arrows in the figures. So the arrows indicate the direction of the travel of the AGV. Okay, this is a form to chart, okay, to understand how the AGVs travels from one station to another. So the first value on the left indicates the flow rates. The second value, which is on the right, indicates the travel distance, okay, between the station. So in this particular numbers, it is a value, okay, this is corresponding values for between session 1 and session 2. Means that the AGVs will transfer or deliver loads, okay, 9 loads per hour, okay, and the travel distance involved is 50 meters. Another example is the AGV travels from session 3 to session 4. Okay, the delivery of load is 2 loads per hour, and involve 85 meters. So the distance is calculated from the figures. Okay, for example, from 1 to 2, it travels for 50 meters. So from section 1 to section 2, it travel from here, which is 10 meter, here plus 30 meter, and here plus 10 meters. So total sum up to 50 meters. Okay, another example is from 1 to 3. Okay, from section 1 to section 3. So it travel from here 10 meter plus 30 meter plus 50 meter plus 30 meter. Okay, so from here 10, 40, 90, 120. So this is 120 meter, and the delivery is 5 loads per hour. Okay, to help us to understand the travels better, okay, so we can develop this network diagram. Okay, let's say I start with station 1, then station 2, 3, 4, and 5. So from the chart, we know that the AGV travels from station 1 to 2. Okay, so the value is 9 to 50, and then it travels from 1 from 1 to 3. Okay, this is 520, and then it travels from 1 to 4. This is 205. Okay, so it's a long distance from session 1 to session 4. You can try to calculate the distance, okay, based on the figure. Okay, so okay, the first one is complete, the first row. Then we go to the second row, which is from session 2 to session 5. So after production, the parts will be delivered to unloading session, which is session 5. So 2 to 5 is here. Okay, so this is 980, and then we go to the next row. Okay, from 3 to 4, 3 to 4. So this is 285, and then we have from 3 to 5. So from 3 to 5. So this is 3170, and the last one is from session 4 to session 5. 4 to 5. Okay, so this is 885. Okay, 8 delivery per hour, 85 meter. Okay, how to find the average travel distance, LD? Okay, so we have to use the formula. So basically we just multiply, okay, the loads per hour with the distance, okay, and then we sum, okay, all the multiplied values. So we multiply first, okay, then we sum up. So for example, the first one is 9 times 50, the second one is 5 times 120, okay, then 6 times 205 plus 9 times 80, this one, plus 2 times 85, this one, plus 3 times 170, this one, plus 8 times 85, this one, and we divided the summation, okay, with the summation of deliveries. Okay, This is 9 from here. 5, 6, 9, 2, 3, 8. Okay. So applying this formula, okay, we will get the average travel distance is 103.8 meters. Okay, in the example 3, this is about a conveyor belt problem. Okay, so we have this single direction belt conveyor. On the conveyor there are third pans. Okay, in this example it says that it takes 20 seconds, okay, to load 18 parts. Okay, 18 parts into each of the third pan, and 4 seconds to load the third pan onto the single direction belt conveyor. So this single direction belt conveyor has a distance of 200 meter from the loading, okay, to the unloading station, and the speed is 50 meter per minute. Okay, for the first question, okay, we have this formula to find the delivery time TD. So TD equals to the distance LD over VC. So this one will be 200 meter over 50 meter per minute, okay, which is equal to 4 minutes. So it means it will take 4 minutes from for the third pan to move from this point, okay, at the loading station to this point, okay, the unloading station. Okay, the next question is minimum third pan spacing, SC. Okay, we need to find the minimum spacing, okay, for the third pans, between the third pans. We have this one formula, the material flow rate, RF equals to RL, the loading rate, equals to the speed of the carrier over SC, and this equation must be less or equals to 1 over TL, loading time. Okay, so what is the constraint means? So the constraint means if we have a worker, okay, which can load parts into the conveyor, okay, with the loading time of 10 seconds, okay, and for 1 minute the loading rate will be 6 parts per minute. Okay, so every 10 seconds it can load a part, and for after a minute, okay, 60 seconds, it can load 6 parts. So let's say we desire to have RL equal to 8 parts per minute. So what happens is the TL will be, TL will be 1 over 8, which is equal to 0.125 minute. Okay, this is minute, equals to 7.5 seconds. Okay, so this 7.5 seconds is much less than the 10 seconds. So 10 seconds is the limit of the worker, so it cannot do faster. So in this case, we cannot achieve the 8 parts per minute. So that's why we have to have this constraint, means that this value, okay, should not be more than 1 over TL, which is the human limits, okay, to load the parts. So in the worst scenario, okay, or the best scenario, let me erase this one first. Okay, I erase this part. Okay, we go back to the formula. Okay, Okay, the best scenario that we can have is the formula can be VC over SC equals to 1 over TL. Okay, so we want to find SC, so we rearrange this formula. SC equals to TL times VC. So from here we can calculate what is the minimum third pan spacing. Okay, so this formula is for NP equals to 1 because we treat the single third pan, okay, as a 1 part per carrier. So this TL equals to 20 second plus 4 second, okay, time BC 50 meter per minute. So to convert this into minute, you have to divide by 60 seconds. Okay, so 60 seconds, 1 minute equal to 60 seconds. So you can calculate this, and the answer will be 20 meter. Okay, so the spacing between one third pan to another is 20 meter. So I will erase this one again. Okay, so the next one is what is the maximum possible part flow rate, okay, RF. So this one we will include these parts, okay, that will be placed inside each third pan. So we have this formula for NP more than 1, which is the flow rate is RF equals to NP times VC over SC. Okay, so NP is 18 times VC is 50 meter, okay, 50 meter per minute, okay, over SC. So we have calculate the SC, which is 20 meter. Okay, solving for this one, we will get 45 parts per minute. Okay, so means that in each third pan we have 18 parts. Okay, after a minute the flow rate will be 45 parts per minute. Okay, the last one, again I will erase this. Okay, find the maximum unload time TU. So we have this constraint, which is the unloading time TU, okay, must less than TL, less or equal to TL. So in the we know that if TU more than TL, what happen is the time to remove the parts, okay, at the unloading station is lower than the part loading into the part loaded into the third pan. So what happen is, if this one is lower, okay, means TU is higher, the third pan will be accumulate, okay, it will have a kind of traffic over there, so it's kind of overflow scenario. So that's why we the ideal scenario is we should have TU less than TL. Okay, TU less or equal than TL means that we have to remove or unload the parts faster than the operator loading the parts. Okay, And the worst scenario, okay, we have TU equals to TL, okay, means that the rate of unloading is equal to the rate of loading. So this one can be TL is 20 seconds plus 4 seconds, okay, equal to 24 seconds. And you can convert it into minutes per pen. So you got this value. In example 4, the problem is to compare between two storage strategy, okay, between the randomized storage and the dedicated storage. Okay, before that, what are the difference, okay, between the randomized and the dedicated storage? So for randomized storage, the incoming items are stored in any available location, okay, normally to the nearest available open location. It adopts first in, first out policy, means that the first item come in will be the first one that will be taken out, okay, or to be used. So for this strategy, it will it will use less space, okay, compared to the dedicated storage. In dedicated storage, the incoming items are assigned to specific location in the storage facility. So there are three bases for deciding the location, based on the number sequence, according to activity level, according to activity to space ratio. So for example, if the items mostly are the most active items, you use regularly, okay, in the production, then it will be placed close to the production stations. So this strategy will use up a lot of storage, but then it has the highest throughput, okay. So the question is, suppose that a total of 50 SKU must be stored in the storage system. For each SKU, average order quantity equals to 100 cartons, okay. The average depletion rate is 2 cartons per day, and the safety stock level is 10 cartons. So if we refer to the figure, we can see that this is the borderline for the safety stock level, is 10. And for when a new incoming items, okay, new items come in, the stock will be replenished, okay, so becomes 110. So this is a minimum level, okay, of inventory. This is the maximum level of inventory, 110. So each carton requires one storage location in the system. Based on this data, each SKU has an inventory cycle that lasts 50 days, okay. So since the depletion rate is 2 cartons per day, so after 50 days, it will reach to the safety stock level. Since there are 50 SKU in all, management has scheduled incoming orders so that different SKU arrive each day. So determine the number of storage locations required in the system under two alternative strategies. Okay, for the randomized storage, okay, we have to find the average inventory level, where the formula is maximum inventory level plus minimum inventory level divided by 2. Okay, so the maximum is 110 plus 10 divided by 2 is 120 over 2 equal to 60. So that's why here the line is created, okay, to indicate the average inventory level. And then the number of storage required equals to, okay, 50 times 60, which is equal to 3000 storage. Okay, so 50 times 60 carton equal to 3000 storage locations. Okay, for the dedicated storage strategy, okay, so each SKU must have its own location. So we have 50 SKU, and then every at one time there will be 110 cartons. So by multiplying these two values, we will get the the answer is 5,500 locations. Okay, as an assignment, okay, please create the from to chart, okay, from this network diagram, as well as the AGV layout for the production system. Okay, so there are 4 stations, 1, 2, 3, 4. This is the loading station 1, and there are 3 production station 2, 3, and 4. So please create the corresponding from to chart as well as the AGV layouts for the production system. Okay, this is example 5, okay, not 6, carousel sizing capacity. So the question is, the overall of carousel storage system has a length of 12 meter. So the length of this carousel is 12 meter and the width is 1 meter. Okay, there are 70 carriers. So these are carriers 1, 2, 3 till 75. Okay, space equally spaced around the oval. Suspended from each carriers are 6 bins. So each of the carriers, okay, has a suspended bin. Okay, so like this. So each carrier carries 6 bin. Right, and each bin has volumetric capacity of 0.026 meter cube. So determine volumetric capacity of the storage system. So first we need to find the total number of bins. So we know that the carousel has 75 carriers, and each carrier has 6 bins. So we have 450 bins, and the volumetric capacity, okay, for all the bins equals to 450 times 0.026 meter cube equals to 11.7 meter cube. Okay, the next question is to find the circumference of the storage system. So this is the formula. Basically, C equals to 2 times L minus W plus W times pi. Okay, so L is 12 minus W 1 meter, so times 2 plus W pi, so W is 1 pi, equals to 25.14 meter.